Well, let's begin. So the first topic I would like to tell today is about the binomial formula. Binomial formula for Schur functions, for Schur polynomials, it's better to say. So let me remind you the well-known Newton binomial formula. Newton binomial. Let's write it as follows. And what we get, this is, and we want to expand this in the powers of x. So this is well known, of course. So we can write the binomial coefficient, and I recall my notation. It's maybe more general. Take a formal variable y, and the falling factorial power is defined as follows: y times y minus 1, and we have m factors, so the last factor is this one. And in this notation, our binomial formula can be written as follows. This is very simple, of course, but let's look at the properties of this expression. It's a polynomial. It's a monic polynomial. It's a monic polynomial. In the variable y of degree m, and its characteristic property is some vanishing property, meaning that it vanishes at m points So let's fix these properties. And now I want to generalize this formula, the binomial formula, for Schur polynomials. So I replace a single variable by n variables. And also I want to replace this object, namely the monomial, by short polynomials. So what I want to do, let's consider the short polynomial. The short polynomial in n variables, and take a shift. And let's normalize it. That is, divide it by the same expression, but for x is equal to 0. So this one, what we get? So the denominator is simply a number. This is a number. We will see that it's non-vanishing. It does not vanish, of course. And the numerator is also a polynomial, and it is a symmetric polynomial of a degree, a number of boxes in lambda. So it can be expanded in the basis of short polynomials. So we want to expand it. So we want to write it as a sum over short polynomials, in n variables. And we want to find the coefficients. So what are the coefficients? So we want to compute them. And of course, if n, the number of variables, is equal to 1, then we get the Newton binomial formula. So this is some generalization. And now I would like to tell you what we get. I need one more notation, some notation that I need. It is as follows. Takes any variable, any formal variable, say z, and given a Young diagram mu, I introduce this notation. It's as follows. It can be defined as follows. Take the product over all the boxes of mu, z plus the content of the box. Let's notice some particular cases. If mu is one column diagram, when we get the following factorial power, so this gives us z minus 1, z minus n plus 1. And if mu is one row diagram, then we get the Pohammer symbol, z plus 1, z plus n minus 1, which is usually denoted as, in analysis, in combinatorics, it's usually denoted as follows. In the theory of hypergeometric functions, this is conventional notation. So this is why I write in such a way for an arbitrary diagram. And now I can state the result, and the result is as follows, that this coefficient is actually equal to the following expression. I recall that this is the shifted short polynomials in lambdas. I assume that the length of lambda does not exceed n, otherwise the left-hand side is equal to 0. And it should be divided by this expression. So the result is that the coefficient in question is equal to this one. And so look at this expression. It takes one can say it takes some symmetric form. There is a certain symmetry between these and these. Okay. Of course, here we have ordinary Schur polynomials, and these are shifted Schur polynomials. But except this distinction, we have some symmetry between the x's and the lambdas. Okay, but here we don't have such a symmetry. The x's and lambda, this is an index, and these are variables. But on the right, we have some symmetry. So how to prove? How to prove this? Let's prove it. It's not difficult. The proof. Just use the definition of the Schur polynomial. So we have, I recall this, the Schur polynomial. Write it already in the shifted variables. In the shifted variables. So what we have? The ratio of two determinants. Here we have 1 plus xj to the powers L sub I, and I recall my notation with the usual one that L is related to the lambda by this shift. Okay. And the determinant of order n. And next we have to divide by the van der Monde in these shifted coordinates. But the shift does not affect the van der Monde. This is obvious, but this is important. So we get the usual van der Monde. Okay. This is the first step. Next, let's apply the Newton formula. So we get that this can be written the numerator. Is equal to the determinant. Sorry, this is a bad notation, I'm sorry. So the numerator is equal to what? You have the determinant, and the sum over m1, mn, which are non-negative numbers. And here we have binomial coefficients, which I wanted to write in my notation, and divided by factorial, and this. Okay. J, this. And the next observation is that this expression is skew symmetric. It's skew symmetric. in the variables, which is obvious, I think. Okay. And in particular, it vanishes. It vanishes unless they are pairwise distinct. So we can assume without loss of generality that they are distinct. Okay. And next, the next step is to notice as follows. So assume this and define mu as a Young diagram with the property mu is defined by the property that J is okay. And now the next remark is that this determinant can be written as the sum. So the sum over M can be taken into account this property, the vanishing property. It can be written as a double sum, first over partitions mu, and next by over permutations of these variables, of these coordinates, And so it can be rewritten as follows. We have this, and next we have this determinant. This denominator is symmetric. It does not depend on permutations. And the permutation of the mu, of the M coordinate, give rise to another determinant, which is as follows. So how this happens? This happens because this determinant, the second determinant, stems from this monomial, the product. Oh, there is no product here. No. The product arises from this determinant. It's correct. So we have some monomial, which corresponds to the identity partition for identity permutation. And next, taking all the permutations, we get this determinant. Okay, so we get this. And now let's take into account the van der Monde. So we can write that our expression, our initial left-hand side, is equal to this one. Now we can replace the summation over these numbers by the summation over partitions or Young diagrams. And you get this expression. And here we have the Schur function, the Schur polynomial, which arises from this determinant divided by the Vandermonde. No, this is not the, I'm sorry, it's not quite correct. It's not quite correct. This is only this one. So we get this expression. Okay. But we need to divide by the value at once. How to obtain this value? It can be obtained from this expression already. Indeed, if you want to get just substitute. But if you substitute this, only all the terms vanish except the one which correspond to the empty Young diagram. Okay, so we can conclude. So we conclude that is equal to what? To the determinant, to only one term persists, and this is this factorial power. And what is here? Here is times 0 factorial, this expression, okay? And the next step is to notice that this expression is simply the Vandermonde. We have here factorial powers, but this does not matter. The only point is that we have polynomials, that we have monic polynomials of the same degree, that we need, of degree n-1, n-2, and so on till degree 0. So this is equal simply to, this one. So what we get? We conclude it follows. So we have to divide by this expression, and it is already in the product form, because here is some determinant, but we can replace it by this multiplicative form, and what we get? So we finally get that divided by the value at once, it is equal to the sum over mu. Of course, that we have this restriction, and the determinant of and divided by Vandermonde, so we can put it here, times the Schur polynomials, which we want, times some factor which arises from this expression and this expression. So this factor is actually this one, or maybe write it. So what we have in the numerator, we have this expression. And here we have this one. And one, it's not difficult to see. Let's leave it as a simple exercise, that this is just, this is equal to, this is the same. This is the same. Look that if mu is empty diagram, that the numerator is equal to the denominator, and this quantity is also equal to 1, because it is a product of empty product, it is equal to 1. So this is easy to see. So, and finally we remark that this expression, this is exactly what we want by the very definition. This is the shifted Schur polynomial. So this is the end of the proof. The end of the proof. There are some consequences, some corollary. First of all, we obtained a formula for the value of for this. And it is equal to what? It is equal to what? To this one. Let's rewrite it a little bit in the nice form. It is usually written as follows. One can write maybe some notation I would like to explain it. Here, and L I naught is this one. The result which is obtained in the case when the lambdas are equal to 0. So this is a very nice formula, a particular case of a while dimension formula, because actually the Schur polynomial is a character of a polynomial representation of group GLN, and its value at 1, 1, 1 is the dimension. The dimension is given by this nice expression. Another corollary is some vanishing vanishing property of shifted Schur polynomials. Shifted Schur polynomials. And this property can be stated as follows. Let's regard the shifted Schur polynomials as function on Young diagrams. And the result then is follows. Is 0 unless mu is contained in lambda. But actually we know this because we know that I explained already that this quantity appears in the expression for the skew dimension, the number of paths from one diagram to another diagram. So it's not surprising. But this is another proof. I mean, another proof which comes from this formula. How to prove this? And the idea is as follows. I would like to say, I would like to state some weaker claim. I want to state a weaker claim. This can be proved also in another way, just from the definition, from the very definition of shifted Schur polynomials, but I would like to, this is called the extra vanishing property, actually. The extra vanishing property, the simple vanishing property. Simple vanishing property says the following, that this equals 0 for all lambda for all lambda distinct from mu with the number of boxes less or equal to the number of boxes in mu. So this is the simple vanishing property, and the first one is some more something which, how to better say, some stronger property, let's say, as follows, okay? So how to prove this? I would like to indicate that it can be derived from the binomial formula, because the idea is follows, that this is a polynomial of degree the number of boxes. So all the polynomials which appear on here must satisfy this property. Okay? And moreover, the only polynomial with exactly the same number of boxes is the one with mu is equal to lambda. Okay, this is the idea, and from this one can deduce the claim, the vanishing property, meaning that the idea is that lambda, in order to get some non-vanishing coefficient, lambda should be, roughly speaking, bigger, larger with respect to mu. Otherwise, the coefficient is equal to z vanishes, but this coefficient in this one. So here we conclude if lambda is smaller in the natural sense with respect to mu, that the result is zero. So this binomial formula seems to be not a difficult exercise, but actually it is very important. It's very important, and it can be applied in many situations, and it can be generalized to more general symmetric polynomials up to Macdonald polynomials. And it has some representation theoretic meaning. I would like to very, very briefly explain why it's important. Some details can be found in the paper. Let me give briefly some reference. Some paper by Akunkov and myself. It's about, I forgot. So the idea is to find limits Jack polynomials as the number of variables goes to infinity. I don't want to explain what are the Jack polynomials. These are some extensions, some generalization of the Schur polynomials. So the idea is as follows. We would like to understand what are characters of infinite dimensional groups. So we would like to understand what happens with this function, which we regard as a character, irreducible character of a unitary group. Here it's convenient to regard it as a character of irreducible finite dimensional representation of a unitary group. It's not necessary to assume that lambda is a partition. It can be a signature. It's also possible. And we want to understand what happens if the number of variables goes to infinity. Of course, in such a naive setting, such a naive formulation, it makes no sense. Because even if you substitute 1, 1, 1, we get some expression which goes to infinity. So there is no limit, naive limit. But if you take the normalization, we normalize, that the resulting expression can have a limit. So what is the formulation? We want let n, the number of variables, goes to infinity, and we can assume that this partition or even a signature also varies together with n. So we can assume that lambda depends on n. Depends on n. We want to understand what are possible limits, and we want to get some functions in infinitely many variables. And in our paper, we solved this problem. Actually, it was examined earlier, so we get some possible proof together with some generalization to Jack polynomials instead of short polynomials. And it turns out that the key idea of our proof is to use the binomial formula. And the key idea, which is due to Vershik and Kirov, is as follows. Instead of viewing this as a function of the variables u, 1 and so on, we want to focus on the Taylor expansion of this function about this point, the unity of the group. We just look at the Taylor expansion. And what is the Taylor expansion? Because our function is symmetric, instead of taking the Taylor series, it is quite natural to replace it by the expansion in short polynomials. And so the idea is to look at the coefficients of this expression. So instead of dealing with these complicated functions, we focus on the behavior of this one, which we know are the shifted short polynomials. And this enables us to get the result. I don't want to discuss this in detail, but I would like only to emphasize the value of the binomial formula, which is indeed an important result. So what next? The next topic I would like to discuss is some characterization of shifted short polynomials. The idea is to regard them as a kind of interpolation polynomials. If sometimes it's convenient to switch from shifted polynomials to ordinary symmetric polynomials. So I will use a parallel definition. So instead of this, I will switch to notation. I could write again, these are shifted symmetric. Shifted symmetric in how these are simply symmetric. Well, the idea is just to assume that the variables are related by this shift. So in these shifted variables, we get simply symmetric polynomials, and they are called now interpolation polynomials. Interpolation polynomials. Why? The idea is as follows. So the characterization is, so this is a symmetric polynomial. Symmetric polynomial. Inhomogeneous, of course. Inhomogeneous. With top homogeneous component equal to conventional Schur polynomials. So one can write as follows. Plus lower degree terms, some polynomials of smaller degree. Next, we have that mu vanishes at points, say, so we assign to an arbitrary, we assign to a Young diagram. Okay, so this bad notation, we assign to it this vector. As usual, we assume that so we regard this is a grid. Some multidimensional nodes. The meaning is the same as in interpolation theory. So it vanishes. So the idea I want to continue, vanishes for all lambda which are distinct from mu, and the number of boxes does not exceed this number for mu. And a remark is that the number of conditions, I mean the number of these lambdas which enter this claim is equal to the number of coefficients of a symmetric polynomial. Of degree, which is equal to the degree of this mu. So we know that these polynomials, which are simply rewritten shifted Schur polynomials, satisfy these vanishing conditions. I just gave a proof of this. So the claim is claim that mu is uniquely determined by this property. Maybe it's better to say there are two properties. These properties. Just as in the case of Newton interpolation polynomials. So what we want to say, this is a generalization of a simple fact that this polynomial has the property that it is equal to low degree terms. First property, second property that it vanishes at first m nodes, which are 1, 0, 1. So this, one can say that this is the Newton interpolation polynomials. These are the Newton interpolation polynomials. And these are some multidimensional generalization of the Newton polynomials. And there is a very nice paper by Okenkopf. I would like to indicate it. Some survey paper. Maybe it's better to say, not exactly survey, but expository, it's better to say. Expository paper by Okenkopf. I forgot exactly, but it is easy to see, it is easy to find in the archive, for instance, Newton interpolation. Newton interpolation, something like that, and published in Advances in Applied Mathematics. A very good paper which explains what are interpolation, multidimensional interpolation polynomials in the framework of McDonald theory. And some characterization, some possible, roughly speaking, it explains that it gives some classification of all possible interpolation polynomials under some mild, reasonable assumptions. Okay, but I would like to return to our subject. Now I would like to explain something. Sorry, what is? Okay. Differential difference operators associated with Schur polynomials. The idea is as follows. Take some So we fix n, number of variables. And write this as the Vandermonde. And let f be a symmetric polynomial in n variables. Now I want to define a differential operator. As follows. I will write and then I will explain what I mean by this. This is an operator acting on this space. So what it does, given a polynomial, a symmetric polynomial here, we multiply it by the Vandermonde. Next, we apply these differential operators. This is a symmetric polynomial in these one-dimensional partial differential operators we get, and then we divide by this. And I claim that the result is again a symmetric polynomial. Why? For simple reason, because after multiplication by the Vandermonde, we get a skew-symmetric polynomial. Applying this differential operator, which is symmetric, we get still a skew-symmetric polynomial again, and then we can divide it by the Vandermonde. So this just means superposition. This operator followed by this operator and followed by this one. Okay. Now the claim is as follows. The claim is that this operator, so this is correctly defined, sorry, excuse me. Is diagonalized in the basis. Let me write as follows. Of short polynomials. I recall my notation. I used this some time ago. I mean here that is the number of coordinates does not exceed n, and this is a Schur polynomial in n variables. Not a Schur function in infinitely many variables, but a Schur polynomial. So this, we know that this is a basis. And the claim is that we get our operator acts diagonally in this basis. How to prove? The proof is easy, indeed, but what happens? what happens. So we take this Schur polynomial, and what we have to do, we have to multiply by this operator first. And what we get, so this result in this alternate. Only the numerator of a Schur polynomial appears, which is a skew-symmetric polynomials. Next, we want to apply this. Maybe. We have to apply this expression. But what happens? What happens? This is an alternating sum of monomials. But if you have some monomial, given a monomial, what happens if you apply to it one of this operator? It's just a multiplication by this, but with power, because we have to differentiate, and next to restore the same power, because we multiply again by this. So this results in the appearance of these numbers. I'm sorry, same monomial, it's multiplied. It's an eigenfunction. And using this, we can easily obtain that the application of our symmetric expression to this skew-symmetric expression results in multiplication by some number. And it's easy to see what is this number. It is exactly so. And when we divide by the van der Monte gain, and so we restore our Schur polynomials, but with some coefficient. So it's a division by van der Monte. And finally, we get exactly this. Polynomial. This is a very good result because we can construct in this way some algebra, some commutative algebra of differential operators, which are diagonalized in our basis. This is simple in our situation. In our situation, it's simple because we have explicit formula for Schur polynomials. But why this is important? This is important because this picture can be generalized to more complicated situation, namely the situation with McDonald polynomial, and Jack polynomials. And for these polynomials, there are no such simple expression as for the Schur polynomials. And then the possibility to produce some differential operators in the case of Jack polynomial, of some Q difference operators, as in the case of McDonald polynomials, gives us some powerful tools for working with, say, Macdonald polynomials. So this is why I would like to tell you about this. In this situation, this is a toy situation, toy picture, but its meaning is that it indicates some way of generalization, which is important. One more possibility, which is sometimes also useful. So it's as follows. Instead of differential operators, one can use Q difference operator or simply Q shift operators. Use of Q shift operators. And again, we can construct some algebra of commuting commuting operators, which for which our basis of Schur polynomials is an eigenbasis. So what is this? And this is especially important in the case of Macdonald polynomials. So what is the Q shift operator? In one variable case, so Q is some parameter, non-zero parameter. This operator acts on a function in one variable simply as follows. We multiply the argument by Q. If you have a function in n variables, we can introduce a partial version, which is as follows, which means that we take and the variable number I is multiplied by Q. All other variables remains intact. Now I can introduce some toy version of Macdonald operators. Toy because they have a simple form in the case of Schur polynomials. It's defined as follows. Actually, we can construct a whole family of polynomials as follows. So let's Z be an extra parameter and defined the operator, an operator as follows. Acting on, so D will act in the algebra of symmetric polynomials as follows. Again, at the last step, we divide by the van der Monde. Here we take the product. So again, first we read this from right to left. So first multiply, then apply this object, and then divide by the van der Monde again. Again, this expression is some operator which is symmetric in this guise. It is symmetric, so it preserves the space of symmetric and skew-symmetric polynomials, and multiplication by the van der Monde gives skew-symmetric polynomials. Applying this, we remain in the space of skew-symmetric polynomials. Then we divide by this, and again we get symmetric polynomials. And again we have it D diagonalized. The basis of Schur polynomials. Actually, this expression is not a single operator. Or maybe we have a free parameter, z. We can expand this expression in the powers of z, okay? And expand it, we can say with this product. What it is? It is the sum and we have an elementary symmetric polynomial in these objects, these operators. They commute, pairwise commute, so there is no problem to define it. So this is actually, one can regard this expression as a kind of generating polynomial, generating series, generating function for this object. Okay. And again, one can easily prove that Schur polynomials are common eigenfunctions of all these operators. And moreover, they are the only polynomials which are eigenvectors for all these operators up to scalar factors. This is because we have sufficiently many operators here. The remark is this one. And these operators are sometimes very useful. We have differential operators in the case of Schur functions, and we also have these two difference operators. Both kind of operators are useful. In some situation, it's we have to use differential, some cases difference operators. And this happens because the Schur polynomials are on the intersections of various families of symmetric polynomials. One family is that of McDonald polynomials with two parameters, q and t. And in the case q is equal to t, the McDonald polynomials does not depend on these parameters, and it reduces to the Schur polynomials. And another family, another kind of deformations are the so-called Jack polynomials. And for Jack polynomials, one can use differential operators. And these operators can be effectively used for the very definition of Jack polynomials or respectively McDonald polynomials. That's why it's truly useful. And what next? What next is I would like to, we have a bit of time. The next topic I would like to briefly discuss, it's simple. This is the principle specialization. Maybe it's a principle Q specialization. I recall that by a specialization of the algebra of symmetric functions or symmetric polynomial, I mean a multiplicative functional, that is a homomorphism in the ring of, say, real numbers or the base field. It depends on the situation. The principal Q specialization for is the algebra homomorphism. We say to R. So we assume that Q is a real number, or it can be a complex number, does not matter. Just we specialize the variables. Specialize the variables. The geometric progression. So there is a nice formula which says the following. We take a Schur polynomial and specialize it. Oh, sorry, whatever. So this can be computed. This can be easily computed. And the result is as follows. I explain the notation in a moment. And this is, I think, the McDonald notation. It is defined as follows. This is the sum. Formally to infinity, but actually it is a finite sum. So this just means that we the sum is finite because we have finitely many coordinates. So this is a beautiful formula. I will briefly indicate the proof. It's easy. It's easy to prove. So how to do this proof? Just use the very definition of a Schur polynomial. So what we have to, so this is the determinant. In place. Now, the nice idea is that this determinant can be computed at once. The idea is to switch this and this. In the initial situation, we regard this quantity as variables, but we can equally well take as variables these ones. And if you do that, we get the Mandelbrot. So this is a simple but very nice idea. So we can say that this is equal to the Vandermonde divided by the same Vandermonde, which corresponds to the empty diagram, zero partition. Let me use this notation. But now we write this as a product of differences, and after simple manipulation, almost trivial, we get this. And from this expression, it's easy to obtain the formula, some corollary. You obtain another proof of the y-dimension formula. Another proof of this formula. The idea is just to take the limit. Take limit as q goes to 1. As q goes to 1, we get from the geometric progression this one. And it's easy to compute the limit here. And we get this expression. And let me also state, maybe I will state it as one of the problem without proof, another form of Q spatialization is as follows. It can be written as follows. This quantity n of lambda appears in many, many formulas of combinatorics. The product of the boxes of our diagram, 1 minus q to n, this is n which appears here, n plus the content of the box. And here we have 1 minus q to the hook length, which correspond to the box. I recall the picture. We have a Young diagram, a box, so we have the hook, and its length is denoted. The hook length is this one. And as a limit, we get another expression for the y-dimension formula. It is equal to the product of the boxes. Divided by the product of the hook lengths. So this is a very nice formula because it can be also written as follows. This is the same as, in my notation, the dimension divided by the factorial. So look at this. This expression is the combinatorial dimension, which is related to the dimension of the character of a symmetric group, And this quantity is the dimension related to GLN or the unitary group. So there is some similarity between symmetric group. In fact, in many situations, there is some connection, some similarity, especially in the case of asymptotic representation theory, as the number of variables goes to infinity, between the symmetric group picture and the unitary group picture. And it is reflected in this simple formula. Okay. So let me stop at this moment.